Anyway, let's get to it. Here we go. We're actually going to start by looking at the periodic table. So I want to talk about them. There's some things about the periodic table. So let me pull that up. So you should have a periodic table that I gave you in lab yesterday. Grab that thing. We're going to write some stuff on it. You're also going to want the periodic table out as we do nomenclature. So you want to have that out in front of you. This is the exact periodic table that you're going to get on the tests. Notice it has the elements names there. I'm fine with that. I'm not going to make you memorize the elements. You are going to have to memorize some polyatomic ions. It's just the nature of the beast. But you know, I mean it. Oh, okay. But yeah, this is the periodic table you're going to get. I would practice with this one. This is the one you'll see for tests. So this is the one I would have out when you're doing homework assignments and stuff. Man, so I want to talk about some parts of the periodic table. We'll get into Dmitry Mendeleev and how he figures this all out in a week or two. But the most important thing on the periodic table right now, we're going to need this for tonight, is I want you to put a staircase on your periodic table. And the staircase is going to have two functions. Let's draw that staircase first. So you're going to go down the left-hand side of boron, and then we just go down, over, down, over, down, over, down, over, down, over, and down. We're going to talk about the main function of this staircase right now. And the main function of this staircase is that it separates the metallic elements from the non-metallic elements. So the metallic elements, with one exception, are to the left or beneath that staircase, and the non-metals or non-metallic elements are to the right or above that staircase. The only exception is hydrogen. Hydrogen is not a metal. There is no good place for hydrogen or helium. Some people put hydrogen here, some people put hydrogen here. If it was up to me, and someday maybe it will be, but if it was up to me, I would put hydrogen and helium off by themselves, kind of like how we offset the lanthanides and actinides down here. I would give hydrogen and helium their own little like spot at the top, not even on the table. But hydrogen is not a metal. Please don't think that hydrogen is a metal. We put it over here because there's one valence electron. It doesn't have anything in common with lithium, sodium, potassium, rubidium, cesium, francium. So that's the first thing, staircase. Got to know where that staircase is. That staircase is going to be ridiculously important when we get to naming tonight because, did I hit record? Oh my, oh I did. Okay, good. I think I hit record. Hang on, I better make sure.
Nah, you definitely did.
Yeah, awesome. Thank you. That would totally suck. So that staircase wouldn't be the first time I forgot to hit record. So that staircase is going to be ridiculously important when we get to naming, because ionic compounds are going to be compounds that have something from the left, a metal, and something from the right, a non-metal. And covalent compounds have only non-metals. So that staircase is your guide to figuring out, hey, am I going to name this like an ionic compound, or am I going to name it like a covalent compound? So more on that in about 45 minutes, okay? The other purpose of this staircase is to show you where the semi-metals are. So the semi-metals are any element that borders that staircase with the exception of aluminum. So boron is a semi-metal, silicon, germanium, arsenic, antimony, tellurium, polonium, astatine, and then these guys. They've barely ever been made. You know, they're purely man-made and synthetics. You don't have to worry about them. Aluminum is not a semi-metal or metal. The other name for semi-metal, by the way, is metalloid. I'll write that out. That's kind of the old-fashioned term for semi-metal, but it hasn't gone away. So metalloid or semi-metal. Aluminum is just a metal. So aluminum is the only one of the elements that borders that staircase and is not a semi-metal or metalloid. You could probably infer from the name semi-metal, okay? These elements, other than aluminum, that border the staircase, they have interesting properties because they are on that boundary between metal and non-metal. These guys can have, you know, properties of both metals and non-metals. So usually at this point, I like to list some properties of metals and non-metals. Let me pop that up on the board. I found like the best way to do that is with a Venn diagram, man. I love me a good graphic organizer. Let's see if this marker died. This room here is above my garage. It's up to like 105 degrees when I don't have the air conditioner on, and these markers love to die. What I should do, ooh, that one didn't die though. Didn't get hot enough yet. Um, what I should do is take the markers out with me, but I'm always too tired. I never remember. I want to put the properties of metals on the left, and I want to put properties of non-metals on the right. And then, of course, the semi-metals are going to be elements that have properties that like each. So if you had infinite time here, you could probably think of a lot of these properties, right? So like, what can you tell me about metals? Well, they're good conductors, right? And the non-metals then tend to be like the antonyms. They're like the opposite. So they're not good conductors. They're good insulators, right? And when I say conductor, I mean heat and or electricity. So metals are good conductors of electricity. They're good conductors of heat. Non-metals, not good conductors of heat or electricity. Okay. What are some other things? Metals are malleable, right? That means they can be bent without snapping, right? Whereas non-metals tend to be brittle. Okay. Think of like charcoal, okay, or flakes of sulfur or something like that, or like those are brittle. What else? Metals are ductile. We don't really have an antonym for that, but ductile means you can pull it out into a wire. Okay, it's an interesting property of metals. Metals tend to have a really high density. They tend to be solids at they tend to be solids at room temp. There's only one exception. There's only one metal that is not a solid at room temp. Anybody know the only metal that is not a solid? You can type it in the chat if you don't want to unmute yourself. Anybody know the only metal that's not a solid? It's actually a liquid at room temp. There you go. Excellent, guys. Thank you. Yeah, it's mercury. But all the other ones are solids. Uh, you know, non-metals tend to be gases or liquids. They can be solids as well, so they're all over the place. We actually have an entire family of elements that are gases. That entire family of non-metals that are gases called the noble gases. But their states are like all over the place, right? What else, man? Metals tend to have really high melting points and boiling points. And that goes hand in hand with the fact that they're solids. Non-metals tend to have lower melting points and boiling points. I mean, metals tend to be shiny. We call that a luster. Non-metals tend to be dull. So these are all, I'm sure there are more if we kept thinking about it, but just kind of you can see how they tend to be vastly different from one another, right? Those elements above the staircase tend to be these things. Those metals below the staircase tend to be these things. Now, those semi-metals that are in the middle, they are interesting. So because they're on that boundary between transitioning between metal and non-metal, they can have properties both. For example, silicon. Okay, silicon is brittle, but it's a good conductor, right? It's got properties. So that's what makes those semi-metals or metalloids so special. Cool, cool. Some other things about the periodic table. Some of these other families have names. Let's do this thing. So you guys need to know some of the metallic families. And that first family that I want you to know is this first family, column 1. By the way, on the periodic table, we call vertical columns. We call these guys groups or families. Group/family. Why do we call them families? Because elements that are in the same vertical column, it's going to turn out they have the same number of valence electrons, and your chemical properties actually come from your valence electrons. So because they have the same number of valence electrons, they have similar reactivities. They kind of look alike. They actually even have similar physical properties and chemical properties. So just like members of a family, because they have similar DNA, because they look alike, that's why we call elements in the same group on the periodic table families. There are 18 groups on the periodic table. You can see there are 3 different numbering systems. I like just the 1 to 18 numbering system myself, but then there's a 1A, 2A, 3A, 4A, and there's like a Roman numeral system, blah, blah, blah. So vertical columns are called groups or families. Horizontal rows, and there are 7 horizontal rows, right? 1, 2, 3, 4, 5, 6, and 7. These guys at the bottom, these guys are actually part of 6. These guys are part of 7. So there's only 7 rows. Physicists do think that they can make 2 more elements. Okay, so then we'll eventually hopefully have 8 rows on our periodic table, but for now we just have 7. Vertical columns are called groups and families. Horizontal rows are called periods. They are called periods, and that's where the periodic table gets its name, because it's arranged in rows or periods. Cool. So let's talk about this. Some of these groups have names. Remember, hydrogen is not actually like part of group 1. It's just kind of here. So I'm talking about lithium, sodium, potassium, rubidium, cesium, and francium. The elements in group 1, these are called the alkali metals. The group 1 elements are called the alkali metals. The elements in group 2 here, very similar name. You really got to enunciate. These are called the alkaline earth metals. You got to throw that word earth in there. They're called the alkaline earth metals. And then this block of 30 elements in the middle of the periodic table. So if you box this off, you go scandium to zinc and then down and over. This box of 30 blocks in the middle, these are called the transition metals. And these transition metals all have pretty similar properties, right? And this is where when I say the word metal and you think of like a stereotypical metal, if I asked you to name off some metals, this is probably where those metals would live, right? So copper, gold, silver, titanium, they all kind of live. They're your stereotypical metals here. You need to know 2 non-metal family names. So the family name that you probably already know is group 18. These are called the noble gases. Noble gases. We do count helium. Helium does count as a noble gas. So that is part of that. So helium, neon, argon, krypton, xenon, radon. And then group 17, my personal favorite, because I used to do fluorine chemistry. This family of elements, group 17, these are called the halogens. Halogens. Awesome. So make sure you know those names. If I say, hey, what halogen is on it, then you should know that's a group 17 element, or if you're taking Chem 102, you learn that the strong bases are alkali or alkaline earth metals paired with hydroxide. You got to know these family names. There are more. Nitrogen's family is called the pnictogens. That's spelled with a P. Oxygen's family is called the chalcogens. You don't need to know that for this Chem 101 class. The only other thing I want to mention about the periodic table here are what's going on down here with the lanthanides and actinides. We'll get into this a little more. We get into Aufbau in Unit 6. But the lanthanides are actually part of row 6, okay? They actually belong here, but if we stuck them in there, the periodic table would be 14 elements longer, and you would need like a scroll, right? Like if I said, get out your periodic table, you'd like open up a scroll because it'd be so wide, okay? So that's why, literally, just so the periodic table isn't so wide, that's why we offset the lanthanides and actinides. The actinides are part of period 7. Actinium comes after radium. You literally would insert them right in there. But again, we pull those off the periodic table, so the periodic table wasn't 14 groups longer. Yeah. They're named after the elements that start those rows. So the lanthanides are named after lanthanum, and the actinides are named after actinium, because that's the element that starts those rows. Keep that periodic table handy. We get into nomenclature. Oh my goodness, you're going to be referring to that because we don't have to talk about charges and stuff. But we're going to start by going over the history of the atom right now. Cool. We'll eventually talk about how Dmitri Mendeleev figures out the shape of that periodic table and all that stuff. But we don't even know what molecular weight is yet. So that's coming. Here we go. So what is the history of chemistry? Well, of the 3 non-soft sciences, if you will. Usually the 3 heavy hitters are biochem and physics. I don't even know if I consider biology a science, but anyway. Of the 3 major branches of science, biochem and physics, chemistry is the baby in the family. If you think about it, physics has been around for thousands of years. Even back Aristotle, they're talking about the motion of the planets and heavenly bodies. They're tracking the motion of the stars and stuff. Um, physics doesn't really start to take off till Galileo in the 1600s, and mentioning him really laying down his laws of motion, which then influenced Newton. But physics, really has been kind of practiced for about 2,000 years, maybe even a little more. Biology been around for a long time, right? Since people have been naming animals and stuff. Um, but chemistry doesn't get started till like the 1600s with a bunch of British scientists studying matter. Before the 17th century, chemistry is really just alchemy, and alchemy is not really, we don't consider that to be a real form of science. It's a pseudoscience because alchemy's goal was not scientific. The goal of alchemists was to take matter that was not gold and turn it into gold to get rich quick, right? It's a get rich thing. So they weren't really trying to understand the universe. They weren't really. Now, I will say this: a lot of elements, a lot of compounds, a lot of chemistry was discovered by alchemists, but their motivations were not scientific. So we do not really say chemistry gets started until Sir Robert Boyle in the 17th century. Now, when we get to the gas laws at the end of this course, which is like 5 weeks from now, when we get to the gas laws in like 5 weeks, yeah, you'll learn about Robert Boyle's gas law. He is the first person to relate the pressure and volume of a gas to one another, and he figures out that they are inversely proportional. So chemistry really gets started with him. A bunch of British and French guys studying gases. um, Another giant moment in chemistry happens in the 18th century with two scientists by the name of George Stahl and Joseph Priestley. Joseph Priestley is important for this area, actually. He was like a Quaker or something, and he he fled England because of religious persecution or whatever, and he actually settled in Sunbury, Pennsylvania, not too far from here. Had a lab, and Joseph Priestley is famous for discovering oxygen. Now, at the time, he calls it dephlogistated air. There was another scientist by the name of George Stahl who collected the gas that comes off of burning materials. Now, we now know that gas is carbon dioxide gas, but he didn't know that. And George Stahl collected this gas that came off of burning materials, and he studied it, and he found that that gas like extinguished flames. Now, we now know that the products of chemical reaction can be used to stop a chemical reaction. That's something called Le Chatelier's principle, who was a French scientist. Stahl doesn't know any of that. He says, hey, this gas that comes off a burning material, it actually extinguishes flames. He calls it phlogiston because this gas flowed out of burning material, right? Joseph Priestley in Sunbury, Pennsylvania, not too far from here, he took some mercury ore and heated it up with a giant magnifying glass on sunny days. And what that did is the mercury oxide decomposed, and he collected the gas that came off of it, which is oxygen gas. So he collected pure 100% oxygen gas. And he studied that gas. And what he found is that this oxygen gas, was the exact opposite of that phlogiston stuff. The oxygen gas made flames bigger. It caused a splint that was smoldering to reignite. He said this is the anti-phlogistons, the opposite of what we now call carbon dioxide, and he called it dephlogistated air. You may say, why is this so important? Who cares? Why is the discovery of carbon dioxide and oxygen so fundamental in the history of science? And the major reason is that after these two guys, people figured out, well, man, both these gases are in air. And this is what led scientists to finally realize that air is a homogeneous mixture of many different gases. Before these two scientists, people thought that air was a pure element. It's almost like the Greeks. You had this earth, wind, fire, water, air, like people would have wanted to put air on the periodic table, which now seems silly, right, in the year 2024. But back in the 18th century, that was not silly. And these guys are the guys that kind of figured that out. If you go on to be a chemist, the Priestley Medal is the most prestigious award you can get as a chemist. It is like if you get a Priestley medal, you are like that. Everybody knows about the Nobel Prize, but the Priestley medal, if you're a chemist, that even means more. It's like the Fields Medal in mathematics, right? The Priestley medal is a big deal. Cool. Next up, we have the father of chemistry, and it is a French scientist by the name of Antoine Lavoisier. And Antoine Lavoisier comes up with the fundamental underlying principle of all chemical reactions. This is the bedrock upon which all chemistry, except for nuclear chemistry, is built. So all chemical reactions that are not nuclear reactions, all chemical reactions must obey this law of conservation of mass. This is going to be the foundation that allows us to do stoichiometry tomorrow night, right? And the mole, and predict how much product we can make from this much reactant, and predict how much reactant we would need to make this much product, and do all that beautiful stuff called stoichiometry. Anton Lavoisier is the reason for that. And it's really simple. He essentially says, hey, man, the total mass of what you put in, the reactants in a chemical reaction, has got to equal the total mass of what comes out. Now, again, we may take this for granted that matter cannot be created or destroyed, but in the 1700s, this was not common sense. People said, well, wait a minute, man. If I burn a log, right, and it weighs 10 kilograms, okay, and I burn it, okay, where did that mass go? Right? It lost mass. Mass was not conserved, right? It's much lighter now that I burned it. What people did not realize was that that gas that came off of it had a weight. And Anton Lavoisier and his wife, who, obviously didn't get a lot of credit, but historians think that she did a lot of this work too. Although I think she was like 13 when they got married. It was a different time. It's French. He's French. Got him a break. So anyway, a lot of people think him and his wife did a lot of these experiments, and what they figured out is they said, well, wait a minute, what if we collect the gas that comes off of burning material, right? And we bag it up, okay, and we weigh that gas. And what they realized is, hey, man, if you weigh that charred log and all the gas that came off of it, then mass was conserved. There is that law of conservation of mass going on. So, decomposition reactions, especially where we produce a gas, sometimes this is hard to prove because you got to collect that gas, right? But this is the fundamental. I mean, you cannot destroy mass. And the reason for that is matter is made up of atoms, and unless I'm doing a nuclear reaction, I'm not messing with the atoms, okay, which we're going to get to in a moment. I'm just reordering the atoms. So that's why, of course, if I put in 100 carbon atoms, I got to get 100 carbon atoms out, and their mass is going to be the same, okay, on both sides. So that's super duper important. Anton Lavoisier, not a great guy. Joseph Priestley, the guy who discovered oxygen, they were contemporaries. Priestley went over back to Europe, and he met with Anton Lavoisier, and he told him about this dephlogistated air he discovered. And he said, when I get back to the States, I'm gonna write it up, put a paper out there. And of course, Anton Lavoisier, while Priestley was on the boat back to the States, Anton Lavoisier tried to scoop him. So scooping is when you try to rush a paper out ahead of somebody. So maybe not the most ethical person in the entire world, but law of conservation of mass, super duper important. Okay, so now we need to talk about the atom, right? And I like to do I like to list all the major players. And the first major player of the atom, I actually don't even have on here. So we'll write him on the board. If my voice makes it through this week, I think I'm gonna make it. The other really tough time for me is the beginning of the school year. My fall semester hack class always starts up the same time as back to school night. So I'm talking all day. I talk all night at hack. I talk to the parents at back to school night, and my voice by the end of that week is gone. No, terrible. Anyway. Atomic theory. Awesome. The first model of the atom was what's the word I'm looking for? Proposed by a British scientist by the name of John Dalton. And John Dalton, this is like the early 1800s. John Dalton is rereading a bunch of Greek philosophers. And the idea of the atom actually exists with the Greek philosophers like 2,000 years ago. Atom actually comes from a Greek word, throw an E on the end of atom, you got like atome or whatever. Um, and John Dalton's rereading these Greek philosophers who are talking about matter. And if you went up to a Greek philosopher or John Dalton and you said, hey, what do you think the atom is? I think what they would tell you is if you took like a pure piece of iron and you chopped it up into smaller and smaller and smaller and smaller and smaller and smaller and smaller pieces, you would eventually get to a piece so small you couldn't cut it up anymore. And they would say, well, that's an iron atom. This is this indivisible thing. Now, John Dalton doesn't know anything about these atoms. He proposes that they're solid. They're not. In fact, we now know the atom is mostly a vacuum. So atoms make up everything, but everything is made of mostly nothing. It blows your mind, right? Don't think about it too hard. But John Dalton would have said this is a solid thing. He would have said there's nothing inside the atom, that this is as small as it gets. Of course, we now know there are subatomic particles, electrons, protons, neutrons. There's even quarks and strings and superstrings, and I don't even care about that stuff. I'm not a quantum physicist. That's not my thing. Um, John Dalton in like 1808 puts out a paper, says four things about the atom, right? He says atoms of different elements must be unique in some way. He doesn't know how they're unique, but he says, hey, these iron atoms, they got to be somehow different than like a copper atom. Turns out it's the number of protons, right? But he doesn't even know. I don't know what that is. That's Rutherford. That's going to be like 100 years later. But he says they got to be unique in some way. He says compounds must contain two different kinds of atoms. We got our definition of compounds on Monday night. He says that a chemical reaction must be a reordering of these atoms. He, in 1808, gets a lot of things right. John Dalton, very good at knowing when to stop talking, right? Okay. Because he doesn't try to like say why or how these atoms are different. He just says they must be different somehow. I don't know how. And he admits he doesn't know how, which is pretty awesome. This idea of the atom exists for a few decades, maybe 50 years, 60 years. And then another British scientist comes along by the name of J.J. Thomson. And I've seen it spelled with a P, and I've seen it spelled without a P. And I believe it's spelled without a P. I think he spelled it without a P. And J.J. Thomson discovers the electron. He discovers the electron using a cathode ray tube. Which I'll describe to you right now. A cathode ray tube is just a partially evacuated glass tube with some metallic electrodes on each side. And what J.J. Thomson essentially does is he hooks a battery up to each one of these electrodes. Okay, so he hooks a battery up to here, hooks a battery up to here, and he's able to get a sustained spark to go from one end to the other. And he says, whoa, man, that's weird. He says, hang on, this was a vacuum. There's nothing in here. There's no atoms in here. And yet I'm able to send this spark from one side to the other. And he says, well, electricity must contain something that's in the atom, something smaller than the atom. It must be a subatomic particle that can bridge that gap, right? And he discovers the electron. And then what he does, he says, well, I wonder if this subatomic particle has a charge. So the idea he gets is he applies an external magnetic field. Take a horseshoe magnet, right? Pretend we have a horseshoe magnet. And he finds that the spark bends towards the positive side of the horseshoe magnet. And he knows that opposite charges, because they had studied static electricity before, he knows that opposite charges attract and like charges repel. So this leads him to believe, well, if the subatomic particle is attracted to the positive charge, this subatomic particle must have a negative charge. And based on that, he comes up with like the worst version of the atom ever. Like if you took our modern picture of the atom and you tried to draw the exact opposite of that, the antonym of that, you would draw this. Okay, it is incredible how wrong this is, but you got to give the guy some credit. He tried. So J.J. Thomson's model of the atom looks like this. It is a sphere with a bunch of negative particles embedded in it, the electrons, and he says they are randomly distributed throughout the atom. But then he says, wait a minute, he says matter is neutral. So if I have a negative charge in the atom, there's got to be a positive charge balancing it out. And his hypothesis is that these negative electrons are sitting in a positive jelly, like a positive, like, like kind of like a jello, that's like holding it all together. So he says the atom is this diffuse positive cloud. Now we now know the atom is essentially a diffuse negative cloud from the electrons moving around. So again, this thing is super wrong, right? And he steps back and he looks at his model. He says, this looks like a British dessert, okay, which is plum pudding. Okay, so he calls this the plum pudding model. Sometimes in high school stuff, you'll hear it called the chocolate chip cookie model or something. That's just stupid. Call it what it is. They called it the plum pudding model. This is plum pudding model. Okay. Yeah, it's bad. Oh, is it bad? This only lasts like maybe 20 years. Friend of mine's grandparent had I don't even know where they had it, but they had a chemistry book from like 1910. Okay, and they showed it to me, and it was incredible. They had just like there was a little tiny paragraph on the electron, and they just like started to discover electrons. J.J. Thomson's model must have been the model at the time, and like they just had no idea what they were talking about. So this is around, this is so bad, right? It didn't take long to get disproven. This lasts maybe 10, 20 years. Okay. And the person who disproves the plum pudding model, he's one of the most important scientists that there is. His name is Ernest Rutherford. Big deal. Big, 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 big deal. Let's talk about him. So there's our plum pudding model. Rutherford, actually from New Zealand, probably the most famous person from New Zealand. I don't know. I mean, I don't want to speak for all of New Zealand, but from New Zealand. He's probably got like statues and stuff. He's probably like on stamps in New Zealand, I would imagine. I don't know much about New Zealand other than they filmed the Lord of the Rings there, and Rutherford was from there. He left and did all of his great work in England. But anyway, Rutherford, super bright kid, super duper duper bright. Family kind of realized he was bright. Family was a bunch of sheep farmers in New Zealand. He wrote an essay contest to try to get a full ride to Cambridge and came in second place. And luckily, the person who came in first place got cold feet. So they literally like telegrammed him and said, hey, man, if you can get to Cambridge, you got a full ride, just come on over. And luckily that happened. I can't even imagine how different the world would be without that, because without Rutherford, there's no Einstein. There's no, I mean, people probably would have figured this stuff out, but like, I'm probably not zooming with you right now. Are we 10 years, 15 years, 20 years in the past? It's amazing how much one person can do. The Rutherfords, the Einsteins, the Newtons, the Galileos, they really speed up the scientific progress. Anyway, Rutherford, when he sets out to do this experiment that we're going to go through painstakingly, because it's probably the most important experiment since Galileo's big rock, small rock fall at the same speed. Rutherford, when he sets out to do this gold foil experiment, he actually is thinking that the plum pudding model is correct, and he thinks he's going to prove the plum pudding model. He thinks I'm going to design an experiment. We're going to get experimental confirmation of the plum pudding model. This is going to help validate the plum pudding model. That was his goal. And what he ends up doing is this experiment actually just destroys the plum pudding model. This experiment uses newly discovered radioactive particles. They don't even know what they are. So the Curies, Marie and her husband, are playing around with radiation. They have no idea what it is. They don't know how dangerous it is. They're just having dinner parties and showing the bones in their hands and stuff, and they don't realize they're nuking each other and their kids. It's really sad, kind of what happened there. The Curies, their lab notebooks are so radioactive, they're kept in a lead case, and you have to put on like a full hazmat suit with a little micro Geiger counter if you want to like look through their lab notebooks. That's how radioactive their stuff was. It was nuts. The whole lab they had to be torn down. It's because they were nuking the neighbors. It was not good. But anyway, Rutherford, they don't even know what this radioactive stuff is, but Rutherford gets his hand on a piece of radioactive material that emits a thing called an alpha particle, which turns out is a helium nucleus. So really really small, not a helium atom, just the nucleus. And There's a British scientist by the name of Robert Milken who's able to get the mass of things. And Robert Milken is able to get the mass of an electron through this experiment called the oil drop experiment. And he's able to get the mass of these alpha particles. And he finds out that the alpha particles are 7,300 times more massive than the electrons. So they're way more massive. And that's going to be really, really, really important for this experiment. So let's talk about this experiment. I cannot overemphasize how much I love this experiment and how important it is. I like this figure. So here in the box, we got our radioactive material. So this thing is emitting alpha particles. And the radiation, the alpha particles are just being emitted on very regular intervals. I want you to imagine this is like a tennis ball cannon. Like, you know, that thing that shoots tennis balls, right? And it is just shooting alpha particles all day, every day. And Rutherford designs this experiment. He says, let's take a really thin sheet of gold. So why did they pick gold? Because gold could be stretched super duper thin. It's super duper malleable, super duper ductile. Okay. So that's why they picked gold. They didn't just do it to spend a whole lot of money. This gold foil is so thin, it's only a few, maybe like 100 atoms thick. To put that in perspective for you, aluminum foil that you use in the kitchen, that's about 64,000 aluminum atoms thick. This is only like 100. So can you imagine? It's almost like, I mean, you guys, if you've ever seen gold leaf, you know how thin gold can be. It's even thinner than that. I mean, it is super thin gold. So it's only a few atoms thick. And here's what Rutherford is thinking. Rutherford is thinking this. If we hop back up to the board here. Rutherford's thinking this. We're firing these alpha particles. Again, he doesn't know what they are. They turn out to be helium nuclei. Okay, but we're firing these alpha particles at gold atoms. And Robert Milken said that these alpha particles are 7,300 times more massive than the electrons. So Rutherford imagines that there's only two possibilities if I fire these alpha particles super duper fast at these gold atoms. He says there's only two possibilities and only one outcome. Take a look. The first possibility is that these alpha particles go right through the gold atom, never hit an electron. They go through this supposed positive ether. Okay. And if that happens, they should hit our detector, okay, right on the backside. This detector is like a piece of like silver oxide or something. And they do this in the total dark. And when an alpha particle hits the detector, a little green flash goes off. So these graduate students who were doing this work were starting to lose their mind. They were like staring into these dark void boxes looking for green flashes for like hours a day. They like started to go crazy. So anyway, that's scenario one. Scenario two is this: fire an alpha particle at a gold atom and boop, it hits an electron. And here's the genius of Rutherford. Rutherford said, well, okay, if the only thing with significant mass in the atom are these electrons, and if the alpha particle is 7,300 times more massive than the electron, then that alpha particle should just shove that electron right out of the way. Think about it. Think of something that is 7,300 times more massive than you, right? Like maybe an 18-wheeler. Okay. 18-wheeler coming right at you, 55 miles an hour, right? That 18-wheeler doesn't care about you. It's going to knock you down and it's going to keep going. That was the idea here. Alpha particle is going to say, excuse me, and it's not even going to know it hit anything. It's just going to keep on going, right? So here's the genius of Rutherford. He says, if the Plum-Pudding model is correct, then all of the alpha particles should go straight through that gold foil and they should hit the back of the detector. There should be no deflection. So one of Rutherford's graduate students sets this up because when you get to graduate school, the boss, the advisor, they don't do any work, right? They just delegate all that work, which I guess is that's the setup. Anyway, I never saw my boss in graduate school do anything. Anyway, Rutherford's graduate student sets this up. They're staring into the box, and they start doing it, and all the green flashes are all over here. And they're like, all right, well, this isn't very exciting. But then all of a sudden, after like 100 flashes, they got like a boop over here. And they go, oh, that's weird. We sent it in here, and you hit over here. Anything get much of it? Keeps there. Then all of a sudden, another one. Boop. Another boop. And boop. And they say, this is weird. So now they start to say, well, okay, this isn't just something's going on here. 99% of the alpha particles going right through the atom, but a couple of them being deflected. And then they got the idea to extend this thing, this detector, all the way around the gold foil. And this is where things got crazy. Every once in a while, every once in a blue moon, they would get a boop, almost like the alpha particle came, hit the foil, and bounce back. Crazy. It takes Rutherford and his group 3 months to explain this. 3 months. Okay, they stopped everything they were doing. Every single person in that lab group stopped. They sat around and they tried to figure this out. Okay, and I got to admit, I don't think I'm smart enough to figure it out. When you go into something with a bias, like the Plum-Pudding model, it is very hard to look at it through a new lens and say, what is the data actually telling me? And if you stop and look at the data where 99% of the particles go through, but some bounce back, it becomes kind of obvious. But again, when you're in the heat of it and you're coming up with this for the first time, it's tough. It's really tough. I mean, I've been there, not with anything nearly as important as this, but doing research, it's sometimes the data is trying to tell you, hey, you dummy, here's what's happening, but it's hard to see it. What they come up with after 3 months is our nuclear model of the atom. And the nuclear model of the atom, so this is going to be Rutherford. The nuclear model of the atom says that the electron is randomly distributed in the atom and it has very little mass. They actually say that most of the mass of the atom is localized in the center, in this thing called the nucleus. And this is where most of the mass is. So Rutherford's model says that the negative electrons are on the around this nucleus. He says it's random. Now Bohr is going to come along, Niels Bohr, and he is going to say it's not random. No, they have to be in certain places called orbitals. And then Erwin Schrödinger comes along and just, oh my God, you're going to hate that guy. He says it's even crazier than that. But Rutherford's model is not, in the year 2024, this is not our current model. We call this the nuclear model because it's the first model with a nucleus. And he says this is the only possible explanation for the data that we're getting. If most of the atom's mass is located in a very tiny spot in the middle of the atom, then if I fire alpha particles, which are 7,300 times more massive than electrons, if I fire alpha particles at these atoms, most of the time, those alpha particles are not going to hit the nucleus, and they're just going to go right on through. And that's why all of the dots were hitting the back of the detector. But he says every once in a while, we're going to send that alpha particle in, and it's going to glance off of the nucleus, and that's where you get those crazy, ones that deflect off at crazy angles. Rutherford also theorizes that the nucleus is probably where the positive charge lives. He is credited with discovering the proton. He is not credited with discovering the neutron. He theorizes the existence of a neutral particle in the nucleus because the mass is just so heavy. But one of his graduate students 10 years later, James Chadwick, he is credited with discovering the neutron. What the heck was I talking about? Oh, this is also why it veers off. The alpha particle has a positive charge because it's a helium nucleus. So when the alpha particle gets close to the positively charged nucleus, it like repels, and that's also why you get this whoom, deflection. Even if it doesn't hit it, it even deflects. And then Rutherford said this nucleus is really, 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 really tiny, but every once in a while, once in a super duper crazy blue moon, the alpha particle have a direct shot with the nucleus, and that's when it bounces almost all the way back and it'll hit the deflector on the same side as where the radioactive material was. So this is how he explains that data. It's just a beautiful experiment, and it's a beautiful explanation that they come up with after 3 months. It's not the final product of the atom, but it's way better than what we had. This starts, I mean, all of quantum physics. Okay, once we know there's a nucleus, and then we start talking about the actual structure of the atom, chemistry takes off. I mean, this is like the most important experiment that's been done easily in the last 200 years. I mean, it is a big deal. Big, 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 big deal. So love this experiment. Love the gold foil experiment. Okay, for a picture that's drawn way better than mine. So take a look here. Way better than my drawing. But you can see these alpha particles coming in. Most of them go through. You get some deflections. You get some bouncing back. Here, love this. Picture's worth 1,000 words, right? Okay, if the plum pudding model was correct, no deflection. That's not what happened. So Rutherford came up with the nuclear model to explain the deflections and the bouncing back of the alpha particles. Big deal. Love, love, love it. A lot of times on the test, I'll ask you to explain the gold foil experiment or explain how the gold foil experiment disproved the plum pudding model and came up with a nuclear model. So make sure you know that experiment inside and out. Cool. So here's our modern view of the atom through Rutherford. In chapter 6, we get to talk about the behavior of electrons, which is a lot of fun. But after Rutherford and his graduate student James Chadwick, we know that most of the mass of the atom is located in a ridiculously dense and small region called the nucleus. To put it in perspective for you, the best description I've ever heard is if you blew an atom up to the size of a football stadium, okay, like a professional football stadium, not like a high school football stadium, but like a professional football stadium. If you blew the atom up to the size of a professional football stadium, the stadium would be the size of the electron cloud where the electrons live. And the nucleus would be the size of a fly or like a peanut on the 50-yard line in midfield. I mean, it is crazy. If I wanted to draw an atom to scale on this board, right? I would draw my big atom. The nucleus, I'd have to get out a magnifying glass to put a little speck down for the nucleus. That's how small the nucleus is. It is insanely small, but that's where all the mass of the atom lives. So hopefully you can gain an appreciation for how small the nucleus is and how dense it must be to have all of the mass, 99.99. I mean, the electrons have a little bit of mass, but the protons and neutrons have almost all the mass. To have all that mass localized in such a small place, it's incredible. And that's why it has very special rules, right? There's two forces found in the nucleus that you don't find anywhere else, called the strong nuclear force and the weak nuclear force. That's what holds it together. That's what gets released and created in fission and fusion. It's incredible stuff there. The rest of that space is where the electrons whirl around, and we'll get to all that in Unit 6. So electrons, negative particles, whirl around the nucleus. Protons, positive charges, they're compacted in the nucleus. And then neutrons are neutral particles. that live in the nucleus as well. What do neutrons do? Neutrons always get a bad rap, man. People are always like, what? Neutrons are neutral. Who even cares about neutrons? But they're there to stabilize the atom. They help keep the atoms stable and keep them from being radioactive. So don't hate on the neutron, right? People always hate on the neutron. If you want some numbers, here you go, folks. Protons and a proton and neutron, they each have a mass of 1.67 times 10 to the negative 27 kilograms. Protons and neutrons have almost the same mass. You can see here out to 3 sig figs, they have exactly the same mass. If you go to 4 sig figs, the neutron, I believe, is a little heavier than the proton. And that's where in some nuclear transformations, when you have like a beta particle decay or a positron decay, some mass is actually getting destroyed when you turn a proton into a neutron. That mass turns into energy, right? And Einstein's the guy that said that was possible. E equals mc squared. Energy equals mass times the speed of light squared. Mass and energy can be interconverted. And that's what makes nuclear reactions so crazy and scary. It's not the law of conservation of mass, which all of other chemistry obeys. In nuclear reactions, we don't have to obey that. Here you can see how much smaller the electron is. The electron has a mass of times 10 to the negative 31st. So we're about 10 to the fourth orders of magnitude smaller, 10 to the third, somewhere in there. So electrons are way, way, way smaller, way smaller. Awesome.